What I want to teach you now is induction with divisibility with questions that has multiple index. And what I mean by that is how we have, for example, 2 to the power of 3n rather than just n. So we have 2 to the power of 3n or 4n, etc. So we're just going to learn how that affects the question. All right, that 4 to the power of 2n minus 1 is always divisible by 5. So, firstly, in step 1, we show it's true for n equals to 1. So how do we know it's n equals to 1, not n equals to 0? Because if we substitute in n equals to 0, you have 4 to the power of 0, which is just 1. 1 minus 1 is 0, which is not divisible by 5. So you know it's only true for when n equals to 1 and not n equals to 0. Okay, so substituting in 1, I have 4 to the power of 2, which is 16, minus 1, which is 15, which is indeed divisible by 5. So therefore, this is true for n equals to 1. So I've proven the first starting point. Now, in step 2, I make the assumption that this is true for n equals to k. So remember, that's when we write that is 4 to the power of 2k minus 1 is divisible by 5. And now we change that into an equation. So we say that 4 to the power of 2k minus 1 equals to 5m, where m is an integer. Yeah? Because by multiplying by 5, we're guaranteeing it can be divisible by 5. Now we can move on to step 3, which is to show that it's true for n equals to k plus 1. So we substitute k plus 1 into this. So we have 4 to the power of 2 times bracket k plus 1, and that's why we get 4 to the power of 2k plus 2 minus 1 is divisible by 5. So remember, we start off with this because there's no left-hand side to start off with. And what we need to do is manipulate it to be able to factorize 5 out the front. And the first thing we do with this is we always want to separate this index. If there's a plus there, we want to separate it. So we separate that into 4 to the power of 2k times 4 to the power of 2, right? Because if it's plus, then when I separate them, it becomes multiplied between the bases, minus 1. Now we look back into the assumption that we made in step 2, and we made the assumption in step 2 that 4 to the power of 2k minus 1 equals to 5m. So therefore, by subtracting 5m minus 1, we can say that 4 to the power of 2k equals to 5m plus 1, right? Because we've added that one onto this side. So now I substitute this into here. So I have 5m plus 1 times 4 squared, which is 16, minus 1, okay? Now I don't want you to go, oh, that's 4 to the power of 2k minus 1, and substitute that whole thing for 5m, because can you see how there's a multiply there? So we can't just use that, right? And that's why I'm actually changing this to substitute 5m plus 1 into there. All right, and now I just need to expand. So 16 times 5 just gives me 80m plus 16 minus 1 equals to 80m plus 15. And I can factorize out 5, which leaves me with 16m plus 3. Now remember how I said I want to check if this is an integer? Well, there's no fraction or decimals there, so I can assume, yes, that is an integer. So this is divisible by 5. So therefore, this must be true for n equals to k plus 1. Now in our conclusion, we would write, therefore, 4 to the power of 2n minus 1 is always divisible by 5, but for n is greater or equal to 1. So remember how we worked at the start, it didn't work for n equals to 0. It only worked for n equals to 1, and then this shows us any number greater than that. So you can see here that when we have a multiple index, all that happens is that with here, when you multiply it by k plus 1, you just have to make sure that you multiply the whole thing, the whole k plus 1, by the coefficient in front. So just be careful to do that.